Hello, math enthusiasts, section 5.5, the remainder and factor theorems. This is a lot of stuff all in one section, so just bear with me as we go through all of it. We're going to learn about the remainder and factor theorems. To know about that, we need to know about synthetic division. To know about that, we need to know about long division of polynomials. And it may have been a while since you've even did long division of numbers, so that's what I'm about to do right now to help you just remember. So I'm going to set up a long division problem just with some numbers, and we'll move on to polynomials. And you just sit back and say, yeah, I remember how that goes. That rings a bell. So first we'd say, what do we have to multiply 3 by to get 3? Or how many times does 3 go into 3, right? We take this guy out here, and we look at the first placeholder and say, how many times does this go into that? So we can multiply 3 by 1 and we would get 3. Okay, so that's what we're going to do. Multiply 3 by 1, we put 3 here, and then we subtract. Okay, ringing a bell here. 3 minus 3 is 0. We bring down the 7. Okay, so how many times does 3 go into 7? It goes in twice, or that's the closest we could get. 2 times 3 is 6. Right, and that's what we write next. 2 times 3 is 6. And then we subtract, and we get 1. And then we bring down the 6, and we say, how many times does 3 go into 16? The closest we could get is 5, because 3 times 5 is 15. And we subtract, and we get 1, so then we would say remainder 1, which really means, like, 1 is, we haven't dealt with 1. We haven't said, how many times does 3 go into 1? We haven't divided 1 by 3, so we just kind of say that, like, 1 still gets divided by 3. 3 needs to go into 1 still. So it comes out as 125 and 1/3. That's what remainder 1 means. It's what remains to be divided by 3. Okay, and that's going to happen in polynomials as well. So I'm going to do a long division problem. I'm going to do the same problem with synthetic division, and then we'll talk about the remainder and factor theorems. So let's take this polynomial, x cubed plus 5x squared minus 7x plus 2. We're going to divide that by x minus 2. So very similarly to long division of numbers, we just look at this term on the outside. Specifically, we're just going to look at the x, or the highest power of x that you would see out here, whatever that may be. And then we say, what do we multiply that by to get the subsequent terms here? So x times what is x cubed? X times x squared, and I put x squared here just because it's above the other x squared. It's just kind of keeps track of stuff. So x squared times x is x cubed, right? Just like we said, 1 times 3 is 3, and then we subtracted. We're going to do something very similar. X squared times x is x cubed. X squared times negative 2 is negative 2x squared. And then we subtract. Now, when you look at this step, a lot of people look at this, right? X cubed minus x cubed is 0. But then when you come over here, you forget to subtract it. We're subtracting this whole thing. So we'll subtract the negative 2x squared, which is really the same as adding 2x squared. So 5x squared plus 2x squared is 7x squared. And then we bring down the negative 7x from here. Okay. Now we do the whole process over again. We say, what do we multiply x by to get 7x squared? X times what is 7x squared? X times 7x will give us 7x squared. So 7x times x is 7x squared. 7x times negative 2 is negative 14x. And we subtract everything here in the parentheses. 7x squared minus 7x squared is 0. Negative 7x minus a negative 14x, negative 7x plus 14x, is a positive 7x. And then we bring down the 2 and do it all over again. What do we multiply x by to get 7x? We multiply it by 7. Okay, 7 times x minus 2, or yeah, we're going to distribute it, but 7 times x first, 7x, and 7 times negative 2 is negative 14. Okay, and now we subtract everything here. 7x minus 7x is 0. 2 minus negative 14 is a positive 16. And there's nothing to bring down, so this is what we call the remainder. We're all done here. So we could say remainder 16. Okay. And what that really means is the same thing it meant with the numbers. What we get when we divide this by that is x squared plus 7x plus 7 plus, remember that in the number problem, 1 still needs to be divided by 3, 16 still needs to be divided by x minus 2. Okay? So x squared plus 7x plus 7 plus 16 over x minus 2 is what you get when you divide this by this. It's equal to this, x cubed plus 5x squared minus 7x plus 2 divided by x minus 2. All right? And another way you could look at it is if you multiply 3 by 125 and 1/3, you should get 376. And if you multiply x minus 2 by x squared plus 7x plus 7 plus 16 over x minus 2, you should get x cubed plus 5x squared minus 7x plus 2. Okay. But really the important thing here is that you see the process of long division. Let's do the same process by synthetic division. All right. So the first thing that we're going to do is set up this little L bracket here. And we want to divide x cubed plus 5x squared minus 7x plus 2 by something. So what we're going to put in here is actually the coefficients of each of these terms. The coefficient here is 1. So we're going to put 1. Then we'll put 5 because there's a 5x squared. Then we'll put negative 7 because there's a negative 7x. Then we'll put 2 because there's a positive 2. Then, if you're going to do long division and you want to divide by x minus 2, then you put a positive 2 here instead of a negative 2. Put a positive 2, and you bring down the positive 1. Now you might be thinking that this looks familiar, and it should look familiar. So from section 5.2, synthetic substitution, we use this setup to plug 2 into this polynomial here. But now we can also use it to divide this polynomial by x minus 2. All right? So we do the same exact steps as synthetic substitution, and now we call it synthetic division. And it just has different implications once we're done. So we just take 2 times 1 and get 2. Whenever the computer decides that that's okay to do. There we go. 2 times 1 is 2, and then we add, we get 7. 2 times 7 is 14, and we add, we get 7. 2 times 7 is 14. We add and get 16. So notice what we get. A 1, 7, 7, and a 16. So take a look here at this one. 1, 7, 7, 16. X squared plus 7x plus 7 plus 16 over x minus 2. There's your 1 right there. There's your 7, your other 7, and your 16. So you get all the same stuff out of a much shorter process. Now the only thing is you might be thinking, well, why don't we do this all the time, synthetic division? The only time you can do synthetic division is with this kind of a factor. What kind of a factor is that? It's a factor that looks like this. X to the first power minus something, some number. Okay, it can't be x squared, it can't be x to the third. It can only be an x. Okay. Now keep in mind that just because I've put a subtraction here doesn't mean that you couldn't see x plus something, but if you had x plus something, it would just mean that c was a negative, because we'd be going minus a negative number, and that would equate to addition. Okay, so just keep that in mind. Just whatever that guy is there, you just put the opposite up here, and then you're doing synthetic division. Alright, so what are the remainder and factor theorems? Well, if we divide a function, a polynomial, by one of these kinds of factors, okay, specifically this kind that we just talked about, then the remainder, whatever you get here, or we also got it here, that's what you would get, and it shouldn't be a surprise because this is synthetic substitution here. That is what you would get if you plugged in 2. That's what you would get if you plugged in c into the polynomial. Okay? Now you can read the remainder theorem in the book, and believe me, the way I've explained it is a little bit more clear. I'm actually going to change this to a k, because I chose c, but they have k in the book. We might as well do it the same way and just be consistent. Okay. So that's what the remainder theorem says, and it's not a big deal. If we divide this by this kind of a factor, then the remainder is what we would get when we plug in k to the polynomial. So apparently, according to the remainder theorem, 16 is what we would get if we put 2 into the original polynomial, x cubed plus 5x squared minus 7x plus 2. So that's a pretty cool deal. Now, the factor theorem goes like this. Let's say that when we did this problem, we wound up getting a 0. The factor theorem would say that since this came from, remember, it came from x minus 2, and we put a positive 2 there. Since it came from there, it would say that x minus 2 is a factor of this original polynomial, x cubed plus 5x squared minus 7x plus 2. To show you why really quickly, and this is important to understand, this is one of those times where you could just remember the theorem, memorize it, and use it, but you could strive for higher things to understand why that is. So why is it if we get a 0 here that x minus 2 would be a factor? Let's use a different example because it doesn't come out to be 0. So let's use an example where it would come out to be 0. And let's set up the synthetic division. And we'll make sense of it. We put a 3, negative 4, negative 28, and negative 16. So we're going to do synthetic division on this. What is this dividing? Well, it's dividing, let's see, this must be the constant. So this must be negative 16, and this must be an x, so negative 28x. And this must be a negative 4x squared, and this be a 3x to the third, right? We just keep moving our way up through the powers of x. And we must be dividing it by, let's say we're dividing that by x, what would be there with x? It would be x plus 2, because this is the opposite of what you see there. So we're dividing this by that. Okay, so let's do the synthetic division real quick. We'll just bring down the 3. Negative 2 times 3 is negative 6. Then we get negative 10. Then we get negative 2 times negative 10 is positive 20. Then we get negative 28. No, not negative 28. Negative 8. Right? And negative 2 times negative 8 is 16. And we add that together, we get 0. So there we go. We should at least recognize, hey, this is factor theorem territory. When you get a 0 here, what the factor theorem says is that x plus 2 is a factor, right? And this should make sense because, let's go all the way back to our original long division problem. We said that what you get here, you should be able to take 3 times that, 125 and a third, and get 376. We said the same thing over here. The thing that we got here with a remainder means that we should be able to take x minus 2 times x squared plus 7x plus 7 plus 16 over x minus 2. That's what we got here. And that should be our original that we divided up. So what we should be able to deduce here is that x plus 2 times, okay, so we got to multiply by what we get left here. That's going to be 3x squared minus 10x minus 8. You can always figure this out by saying this is the constant term, and then we can work our way up through the powers of x. That should be equal to 3x to the third minus 4x squared minus 28x minus 16. Okay, and that's the definition of a factor. You have one polynomial times another polynomial equals another polynomial. So these both multiplied together, they are both factors of this guy here. So if it comes out to be 0, there's no remainder. There's no little fraction-y guy left. Nothing, no weirdness. We just end with a constant term, and so now we have two factors. Okay, one polynomial times another. So that's all it's saying. The remainder theorem says that whatever the remainder comes out when you, basically when you can do synthetic division, the remainder that comes out is what you would get if you plugged 2 into the polynomial. So 16 is what you would get if you plugged 2 into that original polynomial. If it comes out to be a 0, if the remainder specifically comes out to be a 0, then negative 2 must be, or x plus 2, sorry, must be a factor of the original polynomial. Okay, and we're going to use these theorems and such to accomplish some things, specifically factoring polynomials. That's what we're interested in ultimately. Okay, well, we'll do some more examples. We'll get into some more specifics in the sample problems video. Thanks for watching.